Okay. Thanks everybody for joining. Let me introduce Fadi. Fadi Botros is a PhD student in the Technical University of Darmstadt. He's currently a research scientist at the Center for the Competence Center, Smart Living and Biometrics Technologies as part of Fraunhofer Institute for Computer Graphics Research, the IGD. And Fadi's main interest is in basically biometrics, and currently he's doing a PhD in embedded biometrics. He published a good number of papers after he started his PhD in 2019. And today he will give us a talk on the challenges and solutions, current challenges and solutions of face recognition. Fadi, thank you, and please go ahead.
Oh, thank you, Wael, for introduction, and thank you again for giving me this opportunity to presenting today. And thank you everyone for joining. In this talk today, I will present some of the recent advances in face recognition, including some of also some challenges that are facing this technology and potential solution for this challenge. This talk I divided into 4 main parts. In the first part, I will give a short motivation for biometric recognition and face recognition, and I will also presenting one of my contribution in this area. In the second part of the talk, I will present an efficient face recognition solution, and also I will present 2 of my contribution also in this domain. In the third part of this talk, I will present one of the recent challenges that face recognition technology, and more specifically here, I will presenting the effect of wearing a face mask on face recognition performance. And in the last part of this talk, I will presenting one of the face recognition subsystem component, and mainly here I will presenting our recent work about face image quality assessment. So starting with a short motivation, one can see the identity and identity proof under 2 types of applications. Sorry.
I'm still seeing your title slide. I don't know if others are seeing.
I changed the slide, so.
I'm here. Are you advancing the slides?
Yes, yes.
We all still see the title slide.
We actually PDF version, so you have the wrong screen.
Maybe I stop the sharing and sharing again. Maybe I can share the whole screen. Is it changing now?
Yes.
Yes.
Okay. Sorry for that. So again, some motivation for biometric. One can see the identity and identity proof under 2 different types of application. First is identity management, as seen by government and law enforcement agency. And this is mainly motivated by the need for user accountability, and it's observed by all of us every day by having an ID card. It can be also seen from law enforcement agency and forensics perspective, such as monitoring a public place. Also, proof of identity is essential for a user to provide a secure access, and it also provides a level of convenience, such as service personalization. Face recognition is one of the accurate biometric recognition solutions that does not require any direct contact with individual in order to perform a recognition task. It has been deployed today in many application scenarios, such as in airport for automated border control and for mobile authentication. Looking on the recent advancement in face recognition in last couple of years, here in this plot, I have put some of the recent works that published from 2014 until today. And I show the accuracy, how it's improved on one of widely used benchmark for evaluating face recognition. It's labeled face on the wild. And we can see, for example, from 2014, the accuracy of LFW by deep face, it was around 97.5. This accuracy today is improved to around 99.8 by most of the face recognition solutions that has been proposed in the literature. However, this is not always the case for all the evaluation benchmark. For example, on IGBC benchmark, one of the recent face recognition evaluation benchmark proposed in 2018, and we see that most of the recent face recognition solutions that has been proposed in the literature achieve around 96 true acceptance rate at false acceptance rate at this database with operations threshold 1E-4. So this leaves a space for improvement. So a very small overview about the face recognition pipeline. Given, for example, two images, these two images are first pre-processed by applying, by align and crop the face object within this image. Then these two images are passed into feature extraction model to get a feature representation. Then these two feature representation are compared to obtain a comparison score. And based on some operational thresholds, the system decide whether these two face images are genuine, that they are belong to the same identity, or they are imposter. So the main goal of the deep learning feature extraction model is to learn the most identity discriminative feature of the input image. The advancements that we saw previously in the previous slide are mostly related to advancement in network architecture, the availability of large-scale training database, and it's also related to the face recognition training loss function. So in the next couple of slides, I will focus on face recognition training loss function, and I will present one of our contribution here. So the main goal of face recognition training loss function is to increase the discriminative power ability of face recognition model by minimizing the intra-class variation and maximizing the inter-class variation. Commonly in the literature, I think the face recognition training loss function can be classified under two categories. The first category is based on optimizing the Euclidean distance between the deep feature representation, and one of the widely and commonly used loss function in this category is triplet loss. The idea is very simple. Given, for example, anchor and positive, two samples that belong to the same identity, and negative is coming from other identity. The training objective of triplet loss to minimize the distance between anchor and positives that are belong to the same identity, such as it's smaller than any distance between anchor and any other negative sample. The second category of face recognition loss function are based on widely used classification loss function is softmax loss. And here we have seen in last couple of years a lot of advancement in proposing what today known as margin or angular margin penalty softmax loss. And here we have one contribution, our loss, it's named elastic phase, and in next couple of slides, I will shortly revisit softmax loss that lead to our proposed elastic phase loss. So softmax loss, it's referred to applying cross entropy on the output of the classification layer and ground truth label. The main limitation of using softmax loss for training a face recognition solution is that there is no restriction on the minimum distance between the class decision boundary during the training. So this is what we see here on the image on the left. And this actually motivates a lot of work in last couple of years to propose what known today is margin penalty softmax loss, which apply a penalty margin between the class decision boundary, aiming at pushing each sample to be close as possible to each center, to its center. So the idea starts from what's known today as cosine softmax loss. Given softmax loss as defined in the first equation, this work proposed that the bias factor of last layer can be fixed to be 0, and the norm of the feature and the weight can be also fixed to be 1. Thus, we can rewrite the softmax loss as defined in the second equation. Actually, there is no advancement here in cosine softmax over normal or conventional softmax loss. The only difference that the decision boundary is dependent on the cosine or angle cosine between the feature and their class center. And what's happened in last couple of years, there are a number of works that propose to deploy a fixed margin penalty between the feature embedding and the class center to push the decision boundary of softmax loss. And this is what we see here in, for example, in these 3 images: sphere phase, cos phase, arc phase. And this margin penalty, it's the idea, it's very simple, but it's proof that it's very affecting by pushing each sample to be as close as possible to each to its class center. What we propose that this fixed when we train with fixed margin penalties, that this work assumes that all samples can be pushed to the same degree to its class center. So what we propose elastic phase. The idea similar to what has been done before. The main difference that we don't apply a fixed margin penalty value, but rather we relax this fixed margin penalty margin by deploying a random margin value drawn from normal distribution. And this aiming at give the decision boundary a space to extract and retract, allowing for flexible class separability. We also propose elastic phase plus. It's extended over elastic phase. And here we consider the allocation of feature representation in the feature space with respect to its class center. So meaning that when the samples are far from their class center, we push it with larger penalty margin. And when the samples are relatively close to its center, we relax this penalty margin by giving less attention on these classes. So here's some toy example. I did train 3 instances of face model under 8 class classification problem with feature embedding equal to 2. And here I present the result, how these features are distributed around their class center by arc phase, by our proposed elastic phase and elastic phase plus. The number inside the circle, it's referred to the angle in degree between the class center and the number around the edge. It's represent the standard deviation, how each sample are far from their class center. And we see that our proposed laws lead to more, let's say, uniformly, that the features are more uniformly distributed around their class center. Putting this result in perspective with recent works at state-of-the-art face recognition solutions that proposed in the literature, we see that our loss did very well job. It's almost outperform the previous work in almost all evaluation setting. So moving to the next second part of this talk, and here I will present our contribution to the efficient face recognition solution. And the main idea of achieving an efficient face recognition solution is that we want to maintain the accuracy of the face recognition model while using limited resource. This resource, including, for example, the runtime memory and required computational operation. It's also include the battery and environment footprint. From an application point of view, the efficient face recognition model is needed for several reasons. This includes, for example, when we have a limited resource, such as in smartphone, or when the hardware cost is very high, such as in automotive domain, and we need to minimize this resource cost. It's also needed to enable large-scale application and to achieve environment-friendly operation. Here we have two main contributions. The first contribution, it's called mixed face net, and the second one, it's called PocketNet. In mixed face net, what's the main idea? The idea is that we need to design a network that capture different patterns from convolution at different resolution. This has been achieved by splitting the convolution input into group and applying different kernel sites on each group. The idea is mainly inspired by MixNet that presented early this year. And based on that, we propose a set of extremely efficient face recognition network. We also propose to extend this mixed convolutional block with channel shuffle operation, aiming at increasing the discriminative learning ability of this efficient face recognition model by allowing to exchange the information between the channel. Some result, what we have achieved and how it's compared to the efficient face recognition models that has been proposed in the literature. So what here I plot on the x-axis the computational complexity in terms of floating operation point, and on the y-axis we have the achieved performance. The models that tend to be on the top left, it will have the best trade-off between the computational complexity and the verification performance. Our model are marked with triangle with red edge, and we see that in almost all cases that our model always tend to be on the top left. So the next work that I have done in this direction, it's called PocketNet. And here we have two main contributions. Our first contribution, it's related to utilizing neural architecture search to design a lightweight face-specific architecture. So we utilize neural architecture search, not based on the general face image, but rather to learn to find the optimal architecture based on face-specific database. And the second and more important contribution here is that we propose a new training paradigm based on the knowledge distillation, what's called multi-step knowledge distillation. Here we want to answer the question, what if we train a neural architecture search based on the data source that are more face specific rather than using a general face image? And what we found that the resulted architecture from the neural architecture search that learn based on the face specific image has outperformed under the same setting when we train the neural architecture search to learn from general face images. In the second part of this work, we propose what's called multi-step knowledge distillation. The idea from the knowledge distillation is to transfer the knowledge from the pre-trained teacher model, that's usually it's powerful and big model, to smaller model to improve the performance of this small model. So what our idea? We propose to further improve this training paradigm by introducing multi-step knowledge distillation. The idea is that the information learned by the teacher at different steps of the training is different than the information learned at the when the teacher are fully converged. And usually when we transfer the knowledge from the teacher at early stage of the training, when the teacher is not fully converged, it's easier for students to learn such information. And when the student is converged, it can be learn more complex information from the teacher. And this is what we see in our multi-step knowledge distillation training paradigm. For example, here we train first the teacher model for X number of iteration. Then we use the weight from the previous iteration to transfer this knowledge to the student one. And we repeat this two steps until the student model is converged. So what we see here to study the impact of this multi-step knowledge distillation on our model performance, we first what we do, we evaluated two models under the conventional knowledge distillation and the one trained without knowledge distillation. And we noticed that, yes, it did improve the performance of the student model or the small model. However, this performance is further improved by applying our multi-step knowledge distillation. Also, put result in a perspective of comparison with the recent work that propose a compact face recognition solution. Here in this work, we focus on the required memory footprint for this compact model. And here we have also plot the trade-off between the required number of parameters for each of this model and the achieved accuracy. And again, some models that tend to be on the top left, it will has the best trade-off between the required memory footprint and the achieved accuracy. And our model, more or less, it always has tend to be on the top left in this plot. So in the third part of this talk, I will present one of the recent challenge that face recognition that's related to the impact of wearing face mask on face recognition performance. As we all know that wearing face mask is today imposed by many country, by many government in many countries to prevent the spread of the disease. And our main research question here to answer whether this wearing face mask is affecting the face recognition performance. To understand, we conduct a small experiment on data that's collected locally. And we found that, yes, it does affect the face verification performance when the subject is wearing mask. This result is also supported by the recent report from National Institute for Standard and Technology, NIST, where they evaluated different algorithms from different vendors on simulated mask face database, and they found also that wearing a face mask affect the face recognition performance. More important, that when the subject is wearing a mask, it has a higher effect on the genuine comparison when it's compared to the imposter comparison. To clarify this point, I have here plot a 3-score distribution. On the left, I have score distribution by comparing unmasked reference to unmasked probe. Both are not wearing mask. And in the second experiment, and what's seen here in the plot in the middle, that the reference are unmasked, but the probe are masked. And we can see here that the genuine distribution is shifted more towards the imposter distribution. Similar conclusion can be seen from the one on the right. When comparing a masked probe to masked reference, both reference and probe are masked, and we got the same conclusions that when either only the probe are masked or both are reference and probe are masked, its effect it has the same effect on the score distribution. And actually, this motivated our solution in effort to reduce the effect of wearing a face mask on face recognition performance. We propose a solution. It's called self-restraint triplet loss. The idea is to deploy small model on top of existing face recognition solution. The input for our model is a face embedding. And what we want to learn, we want to produce another face embedding that look similar to the face embedding of subject when it's not wearing mask, and different than the face embedding from other subject or from imposter one. The first idea that we try to evaluate if we can utilize here a triplet loss that I presented early in this talk. The idea of triplet loss is to minimize the distance between the genuine pair and maximize the distance between imposter pair. So again, giving 3 samples, anchor, negative, and positive, the triplet loss trains the model to minimize this distance between anchor and positive, and to be smaller than the distance between anchor and any other negative. However, based on the evaluation results that I showed in the previous slide, that wearing face mask, it has higher effect on the genuine score. And the triplet loss, it optimizes both distance and ignoring the fact that the distance between imposter score are less affected by wearing face mask. This leads to our proposed self-restraint triplet loss. The idea that this loss can self-adjust its learning objective by focusing on minimizing the distance between the genuine pair, which highly affecting by face mask, when the distance between the imposter one is deemed to be sufficient. Our idea, we conduct experiment on top of different face recognition solution on different database, and we evaluated two different settings. First, by comparing unmasked reference against masked probe, and in the second setting, we compare a masked reference with masked probe, with and without our solution. And here's some result of what we have achieved. And we compare it also with triplet loss as baseline, and we got improvement in most of the experiment setting when we utilize our proposed self-restrained triplet loss. The first case, sorry, it's for when comparing unmasked reference with masked probe, and in the second setting, we compare a masked reference versus masked probe. So in last part of this talk, I will talk about one of face recognition subsystem component, and mainly here I will talk about our contribution to face image quality assessment. Face image quality assessment is a utility of the image for achieving a reliable and accurate face recognition performance. And here what we propose a solution. It's called CRFIQA. It's face image quality assessment by learning sample relative classifiability. I reformulate how we did this solution by answering three main questions. The first question, if we have any given example, and this example was part of face recognition training, which in reality is not, how relatively will be this class to its class center? And the second question here, are the properties that cause the low or high classifiability of training sample are linked with the properties that lead to high or low face image quality? And if it's linked, can we train a face recognition to predict the classifiability of training sample by inspecting internal network observation? So starting by the first one, here's to answer this question, we built it on three main components. We first define a class center angular similarity, which represent the similarity between the sample and its class center. And we see example here on the right. We have two samples that are belong to the same identity, identity 1, and the class center angular similarity is a similarity between this sample and their class center. We also present a scale term, what we called a negative class center angular similarity, which measure the similarity between this sample and the nearest negative class center that belong to other identity. And finally, we define our certainty ratio as the ratio between the class center similarity and negative class center similarity. So after we defining this term, that mainly related to allocation of the feature representation in feature space with respect to its class center and nearest negative class center. We want to answer the second question. Knowing such property, can we use such property as a face image quality assessment? And to answer this question, we plot ERC curve. It's error versus reject curve. It's commonly used metric for evaluating face image quality method. This curve is usual. It shows the effect of rejecting a fraction of image of lowest quality on the verification error. So meaning that when this curve it's drop down, it's meaning when we reject a fraction of lowest images, it does reduce the error. And actually, when we apply it on the training data, so we have a face recognition that is pre-trained, and we calculate the certainty ratio for all sample in this training databases based on this pre-trained model. And we found when we utilize this metric as face image quality, it lead to achieve what's face image quality measure would achieve in this case. So the last question, can we learn this because this information it's only known for training data where the class center is known. However, in reality, the face image quality should process any images without any pre-information about their class center or any such other information. So the last research question, can we train face recognition to learn to predict this classifiability by inspecting an internal network observation? And this is what we achieve by proposing our CRFIQA. And the last research question is that here, can we use this model to predict the face image quality of any given example? And this is what I will show later in our result. So putting everything together, here we have first on the right, is the distribution of the CCS. It's the similarity between the sample and their class center. It's on the blue, and the one on the orange is the nearest negative angular class similarity. What's the idea of plotting this distribution? It's to prove that during the training, not all the sample will be pushed to the same degree to the class center, meaning some sample that will be of low quality will be relatively far away from their class center when compared to high quality sample. What we propose here on the left, it's a complete training paradigm for our proposed solution. So we have a deep convolutional neural network. Then we have at last stage of this network an embedding. And this output of the embedding, we use it to train conventional face recognition model with classification layer and penalty margin. But also we have a quality regression layer. The main idea is that this quality regression layer, there is no label, but it's trained to learn, to inspect what the classification layer has been learned about the classifiability of each sample. So we are training to predict how the sample are allocated in the feature space with respect to their class center and nearest negative class center. And when we put it in the comparison with the recent face image quality method that has been proposed in the literature, here we have the ERC curve, the error versus reject curve. Again, it shows the effectiveness of rejecting a sample of lowest quality on the verification error. And our method, we have two solutions. One we call small and one large. The difference between these two models is training database and the network architecture. The one that red is the small one. It trained based on small network on small databases, and the one on blue are trained on larger database and deeper model. And I just have here an example of one database over 4 models, and we can see that our model performed very well in terms of ERC curve. What also, but last we evaluated here, it's very common in last couple of years to evaluate how the image quality can contribute to face recognition performance when it's used as waiting term for the embedding. And when we compare it with our recent state-of-the-art face image quality method over 4 different face recognition solution, our method improves the performance and achieves state-of-the-art performance on these databases. With this, I end my talk. I hope that I finished on the time.
Perfect. Thank you.
Thank you very much for listening.
Thank you.
I tried to be quick to finish on the time. So sorry if I talk a little bit quickly.
That was perfect. Any questions for Fadi? Okay, I have a question. Fadi, if you can go back to the face image quality slide, it was a few slides back. One more, maybe one more. No, where you have the architecture.
Here?
Yes, this one.
Okay.
Can you explain this a little bit again, please? Is the assumption here that this is closed set or open set? What is the underlying assumption here?
Our assumption, so our basic assumption is that the property that leads as a face recognition model when training any embedding, that this one, it will be the one that of low quality, it will be far from their class center. And the one of high quality, it will be relatively, let's say, close to each class center. And actually, this, I know it's only sample here, but we also prove it in larger experiment. We see here that this CCS, this class center similarity, for the ones that, let's say, visually look good, they have higher CCS. It's meaning that the face recognition was able to push this sample to be relatively close to their center. However, on the one that's shown here that look, let's say, visually of low quality, we see that it have relatively lower CCS value. So if we are talking here about the similarity, it will be smaller. However, this information is only available for training database. It's not available for testing database. To enable this information for testing database, on open set, we don't have a closed set. We add here a regression layer to the network that this layer, it's trained to predict what the network has been observed here about this, let's say, classifiability of or how this sample are allocated in the feature space with respect to their class center. So no, it's open. But
okay.
we learn it internally from other network observations. So we learn what has been the network learned.
So is the upstream CNN pre-trained and fixed, or is it trained?
No, we train it simultaneously.
Okay. So now
while optimizing the class center, we learn what the network has been learned here about how this sample are. Okay.
So during training, if the upstream CNN is not pre-trained, if you actually train it, how do you calculate CCS and Nnccs during training? Where does this come from?
It's during the training. At each iteration, I calculated first the CCS, so I measure it. I know at the beginning of the training, it will not be 100% accurate, but during the training, I calculate it and I use it. So this is calculated here from this. So if we consider the weight, let me re-explain the idea. So we have embedding and we have classification. The weights that connect, for example, the embedding to the first node here is conceptually considered as the center for these classes. And
okay.
if we knowing this information, so we can calculate how the sample are close or far from their class center. And we use this, this observation from the network to optimize the regression layer. So we optimize it simultaneously. We conducted actually experiment on pre-trained model. And what we found that if we have pre-trained model, it's lead, let's say, to less optimal result than simultaneously learning this to optimizing the class center while learning what the network has been learned from during the training.
So it's basically a form of regularization for the network.
Yes, exactly, exactly.
All right, thank you.
Thank you.
This is Pedro. I have a question for you also. So can you speak a little bit about your future work?
What I'm working today. So let's say in my plan currently, so I'm doing two main work. The first work, it's related. So we are trying to prepare and pre-process a large-scale periocular database, as there is no such one in the literature. I'm also open to any innovative work, so I'm always open to new ideas. So this is a quality. I never work with it, but whenever something is interesting, it supports what my research direction, I always open to work on it. We also working on different model compression technique, including layer-wise quantization for deep learning biometric-based solution.
Okay, thank you.
Thank you.
Thank you.
Greg has a question.
Yes, please.
Oh, hi. Yeah, thanks for the talk. I'm not super familiar with the literature and face recognition. So I understand, so for instance, in this plot that you're showing now, that the number of classes is the number of people that you could recognize, which could be a huge number of classes in some cases. So I'm curious about, so in your results, I didn't see much discussion of, the kind of scaling to large numbers of classes and whether there's any qualitative difference. And one point when I was kind of interested in that was that you showed this loss function that you modified to get kind of a more of a uniform distribution on a hypersphere is how I understood it. And I was just curious, does this really work when you go to huge numbers of classes, or not? And are there other parts of what you talked about that are going to work better or worse in this very high dimensional setting, or very high class number setting?
Yes, thank you for a question. It's a bit hard to visualize it in higher dimension, but I suppose it does. So it's introducing this margin penalty between on the distant boundary between during the training between the embedding and their class center. Actually, it does push the sample. So it can be seen also from the distribution when we plot the embeddings, that the ones that belong to the same class tend to be closer to their center, and the one from and far away, let's say, from other classes. Talking about number of identity, I think I have seen some work that try to address this problem for face recognition, especially during the training, because on the operation mode, what's needed from face recognition model is to do the feature extraction rather to do an image classification. And I have seen some work that try, because usually the face recognition training database, it has million of identity, and training such solution, it's usually not only it's hard to optimize it, but also it's computational, very complexity to do sampling of this identity during the training. But if the question, this margin penalty, it's really push, actually, somehow it does. Maybe it's hard to visualize it. Does this answer your question, or did I misunderstand anything?
No, that makes sense. Yeah, I now realize after you discussed it that there were like kind of two parts to this. One is the dimensionality of the embedding space, which is different than the number of classes. But yeah, it makes sense that you can still see that they push apart, even though you obviously can't plot it in a nice 2D plot like that.
Yes. So this just only for visualizing. So it's very hard. So maybe in 3 dimensions it could be possible, but it's higher. It could be hard to visualize it, how it's look like. Especially also here in this very simple toy example, we have embedding of 2 dimensions. So we have only 2D embedding, but in reality, most of the solutions, they utilize a higher dimension of embeddings that may contain 100 or even 500 or more dimension of. So the embedding, it's very big. So the size of the feature vector, sorry, not the dimensions, the size of the feature vector is very big. And here we have size of feature vectors that equal to 2. So it's just to make it visualize, we're able to visualize it. So I draw it here for feature vector of size 2.
Yeah, right. So that makes sense. I guess I would have thought, suppose that the feature dimension is very high. I guess I would have assumed that all of the class vectors would be orthogonal to each other in high dimension.
Yes, you are right. However, when we do this margin penalty during the training, it just to make more penalty on the decision of what the model has been trained. So it's meaning to push the model to make to learn that the embeddings that they should be closer, even if the decision boundary between the classes in higher dimensionality are close to each other somehow.
Sure, I see. Yeah, thanks.
I think Mohammed has a question.
Hey, Fadi. Thanks for the talk. It's a general question. That's something that I'm curious about. Typically in the face recognition community, this idea of having compactness in the embedding space, the classes of one class are compact and close to one another, is typically studied in the face recognition community. And I don't know, is there anything specific about the face data that makes this, particularly of interest or particularly useful, or you think it is a general concept that can benefit any other classification problem?
I think it can be benefit for other classification problem. I did like 1 year or even before I start my PhD, I was trying to play with this stuff. So I did on CFARTIN, this general image data. I trained with softmax loss and trained with margin penalty loss. And for achieving an accurate classification, it may have not like huge benefit as learning the embedding. So if I took the same example here and I apply it to the general image, we will see similar result. So we see that the feature representation are more compactness. They are more close to their class center. So it's benefit more, let's say, in learning more discriminative feature representation about the input. I tested on the classification accuracy. It's more or less, it was same, but on learning feature representation, it does more. So it could be benefit for other domain.
Okay, but yeah, but if it doesn't translate to accuracy, then who cares? I don't know.
I don't know. It's based on the application scenario. It's not only this margin penalty, even triplet loss has been transferred to other idea, and it show it's working in other domain, not only for face recognition. So it's good.
Thank you.
Thank you. Any other questions for Fadi? No. Right. Right, Fadi, thank you so much for the very interesting talk. I think it's interesting and a lot of really nice and innovative work. Thank you. And I don't know if Maura is still on the line.